Today, let's look at a nice, tough kinematics problem. Let's say we're on the moon. So we're not going to use G like on Earth. And we are standing in an observation room, and there's a window that's 2.5 meters tall, and we see a rock go shooting up. Well, it wouldn't make any sound. We would just hear, because it's vacuum, right? And it is in view for 0.295 seconds as it goes up, and that's all we know. And yet, with that information, we can calculate how high the rock goes on the moon. Let's see how to use the kinematics equations to get that. So as I said, we are on the moon. There's a beautiful green rock made of green cheese, of course. It started somewhere below, it's going to end somewhere above, but we see it in view for 0.295 seconds. And that is all we need to figure out how high does it go. Well, we need one more bit of information, which you could easily Google, and that is that instead of G being 9.8 meters per second squared, on the moon it's about 1.625 meters per second squared, or about 0.116 of G on the Earth. I'll put a little m next to the moon and a little e next to the Earth gravity. All right, how do we solve this? Well, here's the basic kinematics equations. V equals V naught plus AT and Y equals blah, blah, blah. I'm going to shuffle that distance equation around a little bit. I'm going to subtract Y naught from both sides and write it as delta Y equals 1/2 AT squared plus V naught T. Because essentially, there are 5 unknowns this way. Reading left to right, the unknowns are V, V naught, A, T, and delta Y, or delta X, or whatever the change in distance is. And if you have 3 out of 5, you can solve it. So your first bet in the toughest kinematics problems is just seeing, do I have 3 out of 5? Well, I don't know what the velocity is when the rock reaches the top of the window, and we don't know its starting velocity at the bottom of the window, but we do know that the acceleration is downward, and it's what I'll call gm. We'll plug in the number later. And the time is 0.295 seconds, and the delta y is 2.50 meters. So hey, we got 3 out of 5, and with that we can solve for the velocity at the top of the window and the velocity at the bottom of the window. Now, I'm going to assume that if you're in a class where they're giving you this hard of a kinematics problem, you probably have access to some kind of equation solver, Wolfram Alpha or Desmos, or there's any number of equation solvers out there. So I'm not going to walk through the grunt work of solving those 2 equations. Let's just assume you can plug in the numbers and get the 2 equations solved and find that what I called V, which is the velocity at the top of the window, is about 8.31 meters per second, and V naught, which would be V at the bottom of the window, is about 8.64 meters per second. And that makes sense. It's slowing down because of the pull of gravity, so it should be slower at the top of the window than at the bottom. All right, now we didn't actually need both of them because our problem is not to find either of those velocities, but how high the thing goes. And so we essentially have a separate problem where we are once again going to look for I'll use a different color just for fun. For v, v naught, a, t, and delta y. But now we want the final velocity to be 0, because when it reaches the top of its height, its velocity will be nothing. And for v naught, we can actually use either one of the two velocities that we found, because we just do a problem where we know its starting velocity and we know we want it to end up at 0. I'll use the velocity at the bottom of the window, 8.64 meters per second. The acceleration is still minus gravity on the moon, which, remember, we would have to plug in that number. The time we don't know, and of course the distance we don't know, because that's what we want to find out. But once again, hey, we got 3 out of 5. It's just a matter of plugging those things into the two kinematics equations and solving once again. Here are the two equations that we're going to plug into our equation solver. I should have written them out for the other one as well. But plugging them into some kind of solver or solving them by hand, we get that t, whoops, there we go, t is about 7.60 seconds, and the height to which it goes is 32.8 meters. Now, the problem just asked how high it went. It didn't say how high above what. So we just want to make sure that we specify that when we answer the question. The rock goes 32.8 meters above bottom of window. And there you go. If the question had specifically specified the top of the window, then we would have subtracted 2.5 from our answer. All right. Thanks a lot. Good luck to you.